Hello there. Welcome to another concept and problem session. So this is a standard topic, and you should be clear about this before you can proceed in more, advanced topics in optics. So today we're going to talk about image formation by reflection. So, what's an image? So if you have some mirror here, so we can talk about three different types of mirrors. So what's the mirror? You have a reflecting surface, and it reflects. You can say it reflects all light. That will be a perfect mirror. There's no perfect mirror, so some light will get through. So this maybe if you have silver, a very thin layer of silver. Now you can't really support that silver, so normally you'll have a glass. So you'll have this is the reflecting silver, and then on this side is air. And then this is a transparent glass, usually glass. It's transparent to the visible light. So if you shine a light, a beam comes in. So a tiny amount will get reflected from here because this is air. Okay. And a lot will get through, and then some will get through, and a lot will get reflected, and then this get reflected. So there will be some back and forth, whole bunch of reflections. But this is mostly what happens. We don't really, when we talk about image formation, we don't go into this detail. This whole thing, we just represent the back end. This back end we represent like this, and the front end we just don't even bother. Usually a glass that's holding the silver is actually very thin. Thinner it is, more high quality mirror you will have, because you don't have this extra effect, or less of it. Yeah, you can always have that effect, but you can have less of it. Okay. In the plane mirror, suppose I put a L-shaped object in front of it. So you can think of this, each point of it is emitting light. Normally you will have some other source of light, and so these are kind of secondary light coming out of every place. So to find the image of this, we can just find where this image of this is, image of this is, image of this. So 3 points is enough. So how do you find the image of 1 point? So you can see from this point, all the rays that are coming from that point will strike the mirror. And we need to know what happens to those rays. Okay, so if I have a point and I want to know fate of one ray, it's very easy. Just take a ray. This is a ray straight perpendicular towards it. So ray number 1. It's going to be just return on the same path. So this is the return ray, and let's call this 1 prime. The return things I'm going to use prime, and original thing I'm going to use unprimed. And then you take another ray. So any of these rays will be fine. That goes from here, any of these rays. So let's say I take this ray. Then at that point, you just apply the law of reflection. So this angle, and then you make that angle and it's going to come out. So this is set 2. So since the image is going to form over here, I'm going to draw it out so that. So this angle is the same as this angle. And so this will be 2 prime. Now 1 prime and 2 prime are not going to meet because they're diverging away from each other. So these are real rays. So we draw virtual rays. We extend this guy backward. So if this is a P, then we call the image. This is the image of object point P. So and this is a virtual image. If the rays were meeting, then it would be a real image. And you will see that in concave spherical mirror, there will be situations in which you will get a real image. So you will see this distance is going to be object distance. And usually you use letter P for that. And this distance is image distance. We'll Q for it. So in terms of not having positive negative values, P is equal to Q. Absolute value, this equal to Q. But because Q is on the other side, so if I was use this as a x-axis, positive x-axis, this will be negative x-axis. So this will be negative and this will be positive. So you say so P was 10 centimeter, then Q here will be minus 10 centimeter, same distance. If you work out the geometry, you can say same distance is equal to Q. This actually is a case of a spherical mirror. You can think of this as a huge spherical mirror with radius of curvature is go to infinity, then focal length goes to infinity. So you can see that these things will be 1 over P plus 1 over Q equals 1 over F, and with F will be half the radius of curvature. So in convex, F is less than 0 and this F is greater than 0. We're going to see this in a minute, okay? So if I do this go to infinity for plane mirror, it's going to be 1 plus P plus 1 over Q equal to 0. And from this also you can say P equals to minus Q. So P equals to minus Q, and this Q is taken to be positive. So this Q, let's say, okay, this Q is, so let's call it like that. Okay, so Q, if I consider a positive number, then if Q is negative number, then Q is negative. Then if P was 10 centimeter, then it's going to minus 10 centimeter, and this all will be well in this sign convention, right? Okay, so this was a kind of baby thing. Let me pause this. Okay, so in plane mirror, things get much more interesting if you have two plane mirrors. So you have a plane mirror here and a plane mirror here, and they are facing each other. So maybe you've seen this situation, and you place yourself somewhere off center, then you can have multiple images. So like from here, you get an image over here. So this is, say, 0, is originally object, this object, and so the image in mirror 1, image in mirror 1, and then there will be another one would be image in mirror 2. But you will find that this serves as an object and to this mirror, because this thing is facing this mirror, and you will get a this distance on the other side over here. This is going to be this image of 2 in 1, and then this guy faces that guy, so this is going to be way out here, image of 1 in 2, and so this is going to go back and forth. There's going to be infinitely many images. Another interesting case is, say at some angle like this, say do 90 degrees. You can try, say if you have 60 degrees, so this is 60 degrees. You can try how many images you're going to get. Over here, if I place something over here, and you draw all the rays, you're going to find that one image will be here and one image will be here. So this is, say, M1 and this is M2. So this is I2 and this is I1. But then this mirror, you can extend it and there will be image over here, image of 1 in mirror 2, and you can similarly extend this guy, and this going to be, it will be at the same place, image of 2 in mirror 1, and there's just going to these 4 images. This is the object, and this is one image, second image, there's a third image, 3 images here, and they're going to keep repeating them. They're not new images are produced, and you can show by just drawing rays. Like you can show that this has information of both mirrors. This one's information on just this mirror, just reflection from here, one ray like this and another like this. It does not have you just mirror 2 information. These 2 rays you can use to find this guy. But to find this guy, you just need the mirror this, and then like that. So find this is also just mirror 1. But to find this, you have to use reflection which reflect from both mirrors. So for instance, if I do this reflection, what's going to go is going to be, this reflection is going to go that way, and that reflection will actually emerge in that direction. So just one, you found that direction, then you need another one. Maybe you do this and it's going to go this way, but this one will go way out there, and then it's going to come out this direction, and you extend them back, it's going to meet over here. You should draw them out. It's a lot of fun to draw them out. Rather than me doing this, I'll say try this, and I'll say you will get 5 images here. And so this is the object, and this should be you can try them out and find out 5 total images. Okay, so that's a plane mirror and some interesting plane mirror things. Let's do a concave spherical mirror. Okay, so here is a concave spherical mirror, which is kind of not bulged out. I like to think of the bulge in, carved out. So this concave is like a carved out, and convex is bulged out. Okay, So here, this is the center of this sphere. I'm just drawing cross section, so it's just drawing 2-dimensional, but the whole thing is 3-dimensional, like a cup, a ball, and the reflecting surface is the inside of the ball. Okay, so this is a we are going to same thing. Say where is the, say this was the point I want to know, which is, this is optical axis. Yes, off the optical axis. So we want to know how to form the image. All right, so this would be you can see from here. So any ray from this, any ray in this, any ray in that, the infinite number of rays that will strike the mirror, and we can use any of these rays to figure out where the image will be. The image of this will be, there are some really convenient rays. So 3 convenient rays that you can actually draw both in both these situations. You just need two. The third one to verify, just verify purposes. Okay, so if something is a spherical reflection, and if this is the center, so if a ray hits that, you can say from the law of reflection, you use what is called tangent at point X, where it hits, this ray hits. And if this is the center, then the normal to the tangent is this line through the center. So this will be 90 degrees. So this will be the angle of incidence. Angle of incidence. So reflection will be just same. So the angle of reflection will be just, the ray will come out this way. So you can see that if I were to send a ray in that direction, then it will bounce. Angle of incidence is 0, which means the angle of reflection is 0, so it's going to bounce right back. So this one ray is very easy to draw. If you know the center, you just go through the center. So if you come in here, then you're just going back 1 prime. That's a very simple ray. What's the second ray we can draw? That's very easy to draw. Well, if we draw at this vertex, then at the vertex, this is the tangent. So the angle of reflection is very easy to get. So just completely symmetric to that is going to come out. So this is my 2, and this is 2 prime. And 1 prime and 2 prime actually meet over here. If you were to put a little bit of piece of paper there, so if I put a piece of paper there, say some paper there, you will see a bright point there corresponding to these 2 rays meeting. You would say, like, how about the other rays? It turns out all the other rays, as long as these angles are small, these angles of, somehow you would say, okay, I restrict the rays by putting that you only go very tiny angle. going big angle here, but not being able to draw. So very tiny ray, only a small amount of rays pass near the. As long as any ray comes in here, we don't know where it will go through the axis at this point. I mean, but all of them will go through that. That's the meaning of image. Every single one of them is going to go through that same point. Every one of them. But to get them, I just needed two of the rays, just two rays. I needed 1 and 1 prime, 1 to 1 prime, and 2 to 2 prime. And figure out 1 and 2 prime, where they meet, and that's where the image will be. Okay? So what's the third ray? Third ray turns out that if I, to get third ray, is parallel to this. You draw a parallel to the axis, a parallel, and that will go halfway between the center and the vertex. So that is going to pass through the focal point on the axis. So let me draw this out because it's kind of a little crowded here. Okay, so take a ray parallel to axis. And it will go through this point. So for that point, there's only one ray parallel to the axis. It turns out, if not that point, but for some other point, if I come through parallel to the axis, some other ray, all these rays parallel to the axis, as if there's a star here far away, and the rays have become parallel, all of this will go through this after striking, and that's why it's called focal point. So this point is called focal point, and the distance is focal length of this mirror. And if this is the radius r, then the distance to the vertex, this FV distance is equal to r over 2. Okay, and there we will talk about sign convention in another lecture. We are going to do this formula 1 per p 1 over q equals to 1 over f, and sign convention in another lecture. Okay, this one I'm going to keep the rays. So this is how to find the for concave spherical mirror. Let me erase and show you another case. Okay, so what we have done is we've done this case where object was outside the focal distance. So if you are within this distance, then you have a different phenomena happens. If you are outside of that, then you get a real image. Here we got real image of P at Q, and if you worked out for O, is going to be on the axis exactly vertically down, and that's can call it the point I. And if you're an object like a arrow, it's going to be like this. If the arrow is up like that, it's going to be inverted like that. Okay, so in terms of image distance, the object distance is, this is the object distance, and this is the image distance, and from the focal point onward, this is the focal length, f. Okay, so now this is the case, you find that the image is not formed on the same side as object like over here. Let's do the arrays and kind of see how this can happen. So those are two special rays for me. So if if the ray from here were to go in the direction of this, it's going to strike the mirror at normal. So this ray will return, this is the A, and it's going to return from there in that direction, 1 prime. Okay, so this is 1, will go into 1 prime. So that's the second one. Is we do it again, say this one, 2. Well, this angle will be, the normal is this tangent, normal is this, so it's going to reflect symmetrically, and it's going to be 2 prime. Well, we can you can see the 1 prime is going that direction and 2 prime is going in that direction. So these are the rays which are actually reflected rays. They're never going to meet, they're going to divert. Very similar to what happened to the plane mirror. And you expect this to be the case because you're close to the mirror, the curvature is less and less important, and so it's more like becomes a plane mirror, but it's still not a plane mirror. And so if I take 1 prime and I go backward, so these are not real rays, these are virtual rays. You go somewhere they're gonna meet. So this is where they're meeting. I'm just gonna call it the image point. So this is where the image will be. So if I were looking from this direction, of course we're gonna see the object, and we're gonna also see something back there. Okay, and that will be the image. Well, not just these 2 rays, every ray that hits this mirror, you know, of course this is going to be, some of these rays will too much angle, so don't want to use that. Maybe you want to use like from here and here. All these rays within this will actually end up coming out in the direction it looks like that. How about the third ray? We can do the third ray. Let's look at this. So third ray is something that comes out parallel and is going to go through the focal point. So this one will go through the focal point. So if I extend this, it's going to meet all the other rays at this point. So this was a real image. This is not where the rays are meeting, so this is going to be a virtual image. This was upside down, so if this was an arrow here, then this is going to be same orientation as that, and it's going to be magnified actually. So this is one way to magnify the image, right? So you can see a virtual image but magnified image. Okay, so this is concave mirror. Again, this happens when the object is in this area. When the object is closer to the mirror surface than focal length. Okay, all right. We can do convex spherical mirror also, just for completeness. And as I've said, the formula that a lot of people use, misuse, we're gonna do this formula in another video, okay? But for now, we're gonna just draw the rays. Okay, so here the situation is also very similar. If a ray comes in the direction of from here, if the ray comes in the direction pointing towards the sea, of course there's no rays going to be here. So So there's no ray there. Okay, so it's going to come in here. The normal will be tangent to that. The normal in the same direction as in a circle, from the center to a point on the circle. That's the direction of the normal, right? So the normal is the same direction, so it's going to come back. So 1 becomes 1 prime. And if the second ray is kind of like, oh, this is kind of hard to draw on this screen. It's going to come out this way. This angle will be the same as that angle. So this is ray 2 becomes 2 prime. And you see the 1 prime and 2 prime are diverging. They're diverging, so I need to go them back. And the 2 prime will actually cross the 1 prime. So this is the 1 prime going backward, and this is 2 prime going backward. 2 prime back, and this is 1 prime backed. And they're going to meet somewhere here. So this is my Q. So this P will appear to be over there if I'm looking in that direction, because these rays, some of these rays are going to come and strike my eye, which all seem to be coming from there. So all the rays in this cone will seem to be coming from here, as far as I'm concerned, you know. So there will be a subset of these rays will kind of hit my eye, and then, you know, it forms its own image, and then that's what I'm going to see. So this is the image I'm looking at. So when you look into the mirror, what you're looking at is the image. You're really not looking at this object, right? So this is the image. Now this image, just like this other image, is obtained by virtual rays. So this is a virtual image. And using the, you know, geometry, the triangles, the similar triangle that occur in this drawing, you can again show that all these three can be captured by 1 plus P plus 1 over Q equals 1 over F with sign convention. So you have to kind of apply sign convention to put them all in one formula, because sometimes it's like 1 over this is positive and this is negative, and so on and so forth, and maybe there's sometimes this positive, this is negative. So that so happens, just for looking, so F will be greater than 0 here, F is greater than 0 here, and F will be less than 0 here as a sign convention, for instance. Now over here, it turns out it's always going to form virtual image. This is always going to form virtual image in the case of convex mirror. This is a convex mirror. And in case of concave mirror, sometimes it's going to form a real image and sometimes it's going to form virtual image. And in the next video, I'm going to try to do what is called algebraic method. We're going to try to find these formulas, and rather than draw them out, once we find these formulas and the sign conventions that go with formulas, you always use the formulas. Okay? So formulas are good for solving problems, but this drawing the rays are good for actually getting a sense of what's going on. So you should have that sense before you actually start to use the formula willy-nilly. Let me show you where we're going. So here's an interesting toy that you may be able to find. Suppose it's made of like two concave mirrors, right? And you put an object here. The dimensions are just right. We're going to talk about this problem in great detail in the future. And you'll see that you'll find that the image is kind of like a hanging. Suppose this is a penny, and the penny will be like hanging right over there, just levitating. So this image is over there, and this like a real, not a virtual image. This is a real image. A real image appear to be right up here. Okay, so dimensions have to be right, and you can find that twice. So we're going to do this problem. That's where we'll end up our discussion for this image formation by reflection. We end up with solving this problem, setting it up and solving this problem. Might take me 1 or 2 more videos to complete this. Okay, this video was longer than I had intended, but if you wish to go check out this my website, physicsbootcamp.org. There are all of this explained in much more great detail. You like this kind of things, you can tell your friends and like and share. You can subscribe this channel. Okay, talk to you later in another video. Bye.